Hi there, and welcome to our introductory lecture on matter. So our key ideas: how can matter be classified? Why are carbon and copper classified as elements? How are elements related to compounds? What is the difference between a pure substance and a mixture? So what is matter, and how can matter be classified? So where every sample of matter is either an element, a compound, or a mixture. So we're going to go through this slide and we're going to talk about these three items, or these three categories, starting with matter. Matter is anything that has mass and takes up space. I think the trickiest example of matter is gas, because it has a mass and it takes up space, but sometimes it's hard to visualize gases or air as being a matter. The next thing we have is elements. So why are carbon and copper classified as elements? So each element is made of one kind of atom, and we can define element as a substance that cannot be separated or broken down into simpler substances by chemical means. So it's the simplest form of that substance that we can have. An atom then is the smallest unit of an element that maintains the properties of the element. So we've got a pie chart here that shows the elements in the human body, and we can see that the majority of our body is made up of oxygen, followed by carbon and hydrogen. And in actuality, this oxygen and hydrogen are probably bonded, so that these two in part can be combined to form water. So I'm not saying water here, so the majority of our body is water, so we're going to have to bond oxygen and hydrogen together to get that. We represent elements by their symbols. Atoms that make up a molecule act as a unit. And a molecule is a group of atoms that are held together by chemical forces. A molecule is the smallest unit of matter that can exist by itself and retain all of substances' chemical properties. So with a molecule, if we consider oxygen, there it goes. So oxygen as our element, which is symbol O. When it is found in nature, it actually is found in its molecular form most of the time. So it's actually found as O2. So this is an example of a molecule that's bonded to itself. So when we look at the periodic table, which is going to be a tool that we'll want to utilize throughout the year, there's some common things that we can see here. So each element is represented by a symbol, and that symbol is either one letter, two letters, or there's some three-letter ones down here also. The first letter is always capitalized. The second or third letter is always lowercase. So I want to make sure that we always capitalize that first letter, lowercase the second or third letter. And then we've got some other information on here as well. So we've got the atomic number, which is on this periodic table, and can be found in different places depending on the periodic table you find. Typically there's a little key, and you want to look at the key to see which one of these items they are. So we've got the name of the element on there, we've got the atomic number, we've got the element symbol, and then we've got the atomic mass. So just some information that's found on there. The periodic table is arranged in increasing atomic number, and yes, it's got this large space, large gap in here, based on how the properties of these elements have been determined. And then we've got these two spaces here, which are technically where this large section at the bottom goes in there. And we'll talk about more in detail in a future lecture what these different elements are called and how they're grouped up. Alright, so how are elements related to compounds? So each molecule of compound contains two or more elements that are chemically combined. Elements combine chemically to form a compound. So again, the definition for compound: a substance made of atoms of two or more different elements joined by chemical bonds. So if we were to think of table salt, which is NaCl, we show the element symbols, and these two items are chemically combined to form a compound. So sodium chloride has a completely different property than sodium and chlorine do by themselves. Sodium chloride, we know, is table salt. It's solid. And then sodium is kind of a shiny silver metal when it's by itself, highly reactive with water. And then chlorine is kind of a yellowish gas, which is highly poisonous, highly toxic. So when we chemically combine those two, you can see that the properties are significantly different. It's safe to consume in moderate quantities, and we use it to flavor foods all the time. Alright, so on this slide we've got some visual representations of the molecule that makes up aspirin, or the compound that makes up aspirin. In order for aspirin to be the way it is, it has to have this formula, C9H8O4. If we change this formula, the C9H8O4, we're not going to have aspirin anymore. We're going to have some different compound or different molecule. So these are just different ways that we can represent this formula. This method uses the element symbols and combines it with little sticks. This one on the top left is referred to as a ball and stick model, so it uses a different color ball instead of the element symbol. And then the upper one, upper right, is a space filling model, and this shows that the oxygens and carbons take up a lot more space than hydrogen does. Compounds have unique properties, and I mentioned this previously, that they've got unique properties from the elements that make those up. We use chemical formulas to represent compounds. So at the bottom here I've got the chemical formula for indigo. So we use C16H10N2O2. So we've got the element symbol, and then the subscript, so the 16, 10, 2, this is how many atoms we have of the element that's shown before. So 16 carbon, 10 hydrogen, 2 nitrogens, 2 oxygens. So if we look at a simpler formula, say we look at water, which is H2O. So this says we have 2 hydrogens, and we've got an O written here, but we don't have any subscripts. When that happens, we assume it to be 1, because we did write the element symbol. We don't have to write the subscript when there's only 1. So this says there's 1 oxygen, 2 hydrogens. Again, we're looking at a space filling model for water. Our formula for water is H2O. And we've got 2 hydrogens that are shown here, and then 1 oxygen, this large one in the middle. Alright, the next thing we're looking at are pure substances and mixtures. So what's the difference between a pure substance and a mixture? So elements and compounds can be categorized as pure substances, and mixtures are not a pure substance. but we can have compounds that are a part of a mixture to where they aren't categorized as a pure substance anymore. Typically, when we find water, or if we take water out of the faucet, it's not pure water. There's some other things in it. So that one tends to be a little trickier, but we can always categorize elements as a pure substance, and for our purposes here, we'll probably specify if we need to categorize a substance as a compound as pure substance. So pure substance is just a sample of matter, either a single element or single compound that has definite chemical and physical properties. And then a mixture is a combination of two or more substances that are not chemically combined. So, for example, if we had water and we put salt in it, we now have salt water, but the salt is not chemically bonded to the water. It's attracted to it, but it's not bonded to it. So we get a mixture. The salt still has its own properties, but we could evaporate off the water and have the salt. We can get the salt back, and evaporation is one of those physical means, and we'll talk about that in a later lecture, how to separate those substances. We tend to categorize mixtures by how thoroughly the substances are mixed. A term here we have heterogeneous mixture, so substances aren't mixed uniformly and they're not evenly distributed. So if we put sand in water, sand sinks to the bottom. If we put oil in water, the two separate out. So we get heterogeneous mixtures because they don't evenly mix. Homogeneous mixture is when these substances are evenly distributed and mixtures are the same throughout. So if we talk about adding sugar to our coffee or put salt in water, then we're getting a homogeneous mixture. So it's even the salt or the sugar evenly mixed throughout that liquid. Miscible is another term, a substance that can be mixed, so salt into water. Immiscible is a substance that cannot be mixed, so oil and water would be an example of an immiscible. And we can also talk about gases are able to mix with liquids as well. If you get a Coke, a soda, Coca-Cola, and you pop it open, it's going to fizz and bubble. What that is carbon dioxide that's actually mixed in that liquid. So here on this slide we've got some examples. This girl's sweater is a heterogeneous mixture. It's mixed with cotton fiber and polyester fiber. At first glance it may look like a homogeneous mixture, but then if we take a closer look, we do see the individual fibers there are kind of separated. We've got a homogeneous mixture here. This is vinegar, acetic acid, and water. So we can see that the vinegar molecule, the acetic acid or vinegar molecules are spread throughout the water. So we call that homogeneous. We also have a sample of water here. We'll say it's purified water, so it's just water. So it's pure substance just made of water. We've got an example of salad, which is heterogeneous as well. And the salad's a little bit easier to see as a heterogeneous mixture than her sweater. And just kind of get a visual of miscible and immiscible. Here we could have, say, water and oil. Toluene is a different chemical, but we'll just say this is oil for our purposes. It's immiscible, so they don't actively mix together. Whereas if we have water and ethanol, they do mix. So they're able to mix that way. Thanks for listening.